Okay, so this is the first introduction to the idea of equilibrium, which basically means balance. And I just want to very quickly really sort of apply some of the concepts that we looked at in the last video to some forces. So thinking about vectors, let's just consider a situation like this. We've got a 5 kilogram mass suspended from a string, and it's being held in place by two strings that are in tension. One of these strings is horizontal, the green string, and there's a tension in that string. Let's say it's T1. We don't know what it is at this stage. It's also held in place by a second string, T2, which is at an angle, some angle against the horizontal. And we need to really, in order to actually do the maths of this, we're going to have to give it some value. So let's just suppose this angle here is 40 degrees. It makes it nice, and well, that's a nice number now. Anyway, so at this stage what we want to say is, what is the tension in T1 and what is the tension in T2? This is all the information you need in order to solve this. You don't need anything else. You need to know one of the forces and an angle, and that's all you need. As long as one of them's at right angles, you need this is the situation. So first things first, this horizontal force does not have a vertical component because it's just a force in one direction. The T2 force though, however, does have two components. It's got a horizontal component and it's got a vertical component. So we can just draw these in now. I'm going to draw in the horizontal component of T2. And just using the stuff we did in that last video, we can say, well, if this is the hypotenuse of the triangle, the imaginary triangle, this is the adjacent side, and basically if it's the adjacent to the angle, it's going to be cosine of this vector. So it's going to be, this is going to be basically T2 times by cos 40. Okay, and then of course it's going to have a vertical component, and we're going to say from that, this is going to be T2 sine 40. Now, once we've done this, we can say, well, there's no vertical components of T1. So if this situation is in equilibrium, i.e. the forces are balanced, then the upward forces must be balanced by the downward forces. So straight away we can set up a little equation to solve for T2. And as we said, the only upward force is T2 sine 40, the only downward force is the weight of the mass. So we could say T2 sine 40 is equal to gravity, let's just say 9.8, let's leave it as 2 sig figs for now, 9.8 times by 5 kilograms. Once we've got that, we've only got one unknown in there, T2, and we can solve for T2. So T2 is now equal to 9.8 times by 5.0 divided by sine 40. Bang that into your calculator, it's going to come out as some horrible number because I've made these numbers up myself. 9.8 times 5.0 equals, divided by, I don't know why I'm even practicing it, sine 40 equals, T2 is now equal to 76 newtons. Ka-ching. I can underline that in red because T2 I've described as my red force. So straight away I just now automatically know the value of T2. If I were to know what T1 is, well, I'm looking at this again. We've already established that the only upward force is T2 sine 40. The only sideways forces, horizontal forces, is T1 and T2 cos 40. So I can do a second statement, and I can say, well, T1 is equal to T2 T2 cos 40. So T1 equals T2 cos 40, and of course we know that T2 is 76 from before. Cos 40 is equal to T1. I just so happen to have my calculator with the 76.23 whatever still in there, so all I'll do is I will multiply that by cos 40 times by cos 40 equals, and T1 comes out to 58.3, let's just say 58 newtons. And there we go, jobs are good. So this really is why vectors are so handy. You've got something and you can basically split it up resolving vectors is so handy. You've got a vector, you can split it into two components, and then you can use it in all sorts of scenarios. I'm going to do one more example very quickly of this. Let's suppose you had a rocket shooting off into space. There we go. Off the ground. And it was going off into space, and it was projected at an angle of, seemed to be doing the same direction, the same angle every time, but let's suppose it's going off at 45 degrees now. Okay, and it's projecting off into space with a velocity of 200 meters per second, ms to the minus 1, and you were charged with the task of running along underneath it and getting a sort of clearly panned photograph of, so you're looking up as you're running along and you're seeing the bottom of this rocket. You'd want to know, well, how fast do I have to go? So really, very straightforwardly, you'd be saying, what does this speed have to be to have the same component, to match the horizontal component of this? Well, of course, this is 45, this is 200, so the horizontal component will be 200 cos 45. Again, could get a calculator, I suppose. 200 cos 45. Bam. 141. So to 2 sig figs, 140. ms to the minus 1. So these vectors just, this idea of resolving components into their vectors just becomes super handy all the time. You use it for all sorts of stuff. Alright, go and do some practice on that, and we'll look in the next video at moments.